Speak to you. You all right? You ready? He's ready.
Good evening and welcome to Monday Night Calculus. I am so excited to be here. My name is Curtis Brown and I have with me Mr. Tom Dick, Dr. Tom Dick, and Dr. Stephen Kokoska. I'm so excited, humbled to be working with these fellas. We've been doing this a little while, so I can give them a little bit of a hard time as we get started. As we get started tonight, go ahead and put something in the chat. Let us know where you're from. I noticed we got a couple of students on. Super excited to see that, and have some folks joining us from all over the country. Hopefully, maybe some folks even from north of the border joining us this evening. That'd be awesome. As we go this evening, feel free to put your questions and comments in the chat. I'll be sure to try to pass those on to Steve and Tom. I will not attempt to answer too many of them on my own. And of course, if you see something in the chat you want to answer to, that would also be fantastic. Finally, one more bit of information here. I would like to just invite you to go ahead and send me an email at the end of the session. I'll be watching for those at the end of the session. I'll put my email up there for professional development credit hours for teachers. Can't help you out, students. Sorry, don't have any professional development for you guys, but I'm so excited that students have joined us this evening. So Steve, I will turn it over to you.
All right, let me give me some permission here to
shoot. Yeah, probably not.
Right.
I got to remember to do that before we get going all the time.
Oops.
Try that now.
All right, looks good. Thank you very much. Let me see if I can get this working. How's that? I'm going to try to make this a little bit bigger. Hang on one second. So let's go to here. And you know what we better do is we better change that. I apologize, Curtis. Let me just change that view a little so that I can write a little bit easier there. Let's do this. Let's see if that works. Oh, I don't like that at all. Holy Toledo. There we go. That's better. Okay. Thank you. Sorry, Curtis. So tonight we're going to talk about particle motion problems, one of our favorite topics. And we start out with, I think, a pretty straightforward problem, but I think some good parts in here. Some little things going on, and we'll eventually get to some technology. And if we have time at the very end, Curtis, we do in fact have a BC problem in here. As we've said many times, we do like to get some BC questions in here too for those students and for those teachers. So here we go. We have a particle that's moving along a straight line. So this is an AB problem for t greater than or equal to 1. The position is given by this polynomial. See if the pen's working tonight. There we go. It's given by that polynomial. And this is my fault, Curtis. I don't pay as much attention as I should to units, but here t is measured in seconds and s in meters. And at time t equals 0, we know the particle is at position 0. So I'm just going to kind of translate that a little bit. So S of 0 is equal to 0. So the first part here, part A, just to get us going a little bit, says find the velocity at any time t. So that, of course, means we're trying to find this velocity function. So in order to do that, we just have to take the derivative of the position function. We do that term by term here because this is a polynomial. So that's ds dt. That's 6t squared minus 42t plus 60, I think. And we're good to go. There's the velocity function. And again, it's good to think about the units. Frequently in these problems on the AP exam, students are asked about units. The velocity here is in meters per second. Very good. Excuse me. Find the velocity at time t equal 3 and t equals 6. Well, we've got to do some translating here from the words into mathematics. You know, in a lot of these particle motion problems, students do have to translate what is the question really asking here? Translate that into mathematics. And here, this simply means I need to evaluate the velocity function at t equals 3 and t equals 6. So I hope you had the opportunity, Curtis, to look at these problems ahead of time. I'm going to plug in t equal 3 into the velocity function, t equals 6 into the velocity function. I've got minus 12 meters per second and 24 meters per second. And while we're here, I might ask throughout this question, I know that the time lag is a little slow here tonight, Curtis, but let's put this one out there. Maybe someone can answer this in the chat. How would you interpret this velocity here at time t = 3? Can you give me an interpretation? What does that mean about the motion of the particle at time t = 3? Beautiful. While you're thinking about that, part C says, well, let's see if we can find all the times t at which the particle is at rest. So what does that mean? We need to find all the places where the velocity is 0. Now be careful. That doesn't mean where the velocity changes sign. It just means where is the velocity 0? Where is the particle at rest? So I still have the velocity function way up top there. I'm going to try to factor that completely. And I think, let me see if I've got this right. I think I took out a 6 out of each of those terms. And I factored that quadratic. I used the principle of 0 products here. And I think I found that the velocity is 0 at t = 2 or at t = 5. And so those are the two times at which the particle is at rest. Cool. All right. Well, a couple of these will get a little bit more difficult. Let's see. When is the particle moving in the positive direction or to the right? Well, what does that mean here? How do we translate this? I have to tell you, Curtis, I was in giving a talk a little while ago, and I got into a good discussion with a teacher in the audience about this, and relating the first derivative of the position with increasing and decreasing. And, whether or not we include the endpoints here. And, we could argue about that all night, but here's what I think is going on. This is my interpretation anyway.
We did get somebody to answer you, by the way.
Oh, good. What was the answer?
I had to prompt them a few times to get them to respond, but we did. It's moving to the left. The negative 12 v of t being negative 12 means it's moving to the left at that time.
Very good. I would encourage you as you think about responding to those interpretation questions, think about all the things that might have to be included in that answer. For example, how do you interpret that minus 12? Well, at time t = 3, the particle is moving to the left at a rate of 12 meters per second. You have to be careful with the minus signs too.
Right.
So think about that a little bit. Very good. Anyway, back to this one, this applied problem. I would not include endpoints here in intervals unless the velocity is in fact positive there. Because I think in this kind of applied problem, you can understand that the particle is moving to the right when the velocity is strictly greater than 0. So I'm going to try to reconcile all of this here in a minute. What I did is this is the way that I like to do these anyway. I take the completely factored form of the velocity, and I'm going to create a sign chart to help me interpret what's going on. And then I will eventually write, I hope, something that would be acceptable on the AP exam. So Curtis, you know that I have all this funny sort of notation for sign charts. And if you can see it on the screen, I have a kind of a bold left bracket there. And the reason for that is that's where the domain starts, and it includes 0. So I know that the velocity is 0 at t = 2 and t = 5. There are my two zeros. I want to know the sign of the velocity in those intervals determined by that 2 and 5. And of course, many ways to do that. Select specific values in those intervals, go back up here and argue generally. And I think I found that I have a positive and a negative and a positive here. Now let's interpret that sign chart. Remember, this kind of a drawing is not sufficient on the AP exam. In my class, it's okay. And I think the answer here is that the particle is moving in the positive direction when t is between 0 and 2, including 0, and when t is greater than 5. And I put down here in parentheses This is the kind of extra information that you would have to include on the AP exam because V of t is greater than 0 during those intervals. Now, I know what you want to ask, Curtis. You want to say, well, what happens if a student is taking the AP exam and they don't include that sign chart, but only come back with this sentence? The particle is moving in the positive direction when t is in those intervals because V of t is greater than 0 during those intervals. You know what? It turns out that in general is acceptable. I'm not sure exactly how the student knows that V of t is greater than 0 in those intervals, but that's the correct justification.
So they don't have to justify that it's positive.
Yeah, that's an interesting way to think about it, Curtis. Yeah, they don't really have to justify that it's positive, but if they tell me that's the justification for those intervals, that's a very good way to think about it.
It's nuanced.
It is indeed. It is indeed. Yep. All right, well, here's kind of not a unique way to represent the motion of the particle, but a way to think about this. Excuse me. Now, look, we all understand that this particle is moving along a straight line, sort of back and forth and back and forth, okay? But here's a way maybe to better visualize the motion of the particle. It starts over here at t equals 0, its position is 0, and you can think of this number line here, this line right here representing the position of the particle. As t increases to 2, it's moving to the right. At t equal 2, it turns around. It's at rest for that one instant and then turns around and heads back to the left. At t equal 5, it's at position s equal 25, turns around and heads back to the right-hand side. So again, that's kind of a nice way to visualize this motion. And with a little bit of luck here in a second or two, Tom might be able to show you that on your calculator. Beautiful. Down at the bottom here, here's a good question. Find the total distance traveled by the particle over this time interval 0 to 4. Well, we have to be a little concerned about where the particle changes direction, where it goes from positive, where it's moving to the right, and then where it's moving to the left. And we know from our previous analysis that it changes direction at time t equal 2. Now, look, I know that there are other ways to do this, but here is a way. I simply find the total distance traveled between 2 time t equal 2 and time t equals 0. I put in the absolute value symbols there because, well, I'm naive about this and I don't really know whether or not it's traveling to the left or the right there, let's say. And then I know at t equal 2, it turns around again. I'll take the absolute value of its position at 4 minus its position at 2. That's 20. I add those two together. I know the total distance traveled is 72 meters. Hey, I got the units in there. How about that? All right, I got a couple of more, Curtis, if it's okay, before I turn this over to Tom. Okay. Okay.
Yeah.
Find the acceleration of the particle at any time t, and then at time t equals 6 seconds. Well, okay. We know the acceleration is the second derivative of the position. It is the derivative of velocity. Pretty straightforward derivatives here. We take the derivative term by term. I think I got a 12t minus 42. And the acceleration at time t equals 6, well, I'm just going to plug that in. I think I got a 30, and don't forget the units here. I didn't ask for them up there, but we'll put them in anyway. I think it's meters per second squared. Now, if you had the opportunity to look at these, I asked you to graph the position, velocity, and acceleration functions, and Tom may have a chance, an opportunity to look at this with you on the 84. But I really like looking at this on the TI-Nspire too, because it does some really cool stuff. If I just enter the position function here, define it, I can actually define the velocity function. I don't have to worry about whether or not I did that correctly in the background by hand. And I can define the acceleration function as the derivative of the velocity. I think that's very cool. And then on the right-hand side here on a graph page, I graph these three. Now, I won't have an opportunity. I could probably spend about a half hour looking at this graph, Curtis, but maybe some of the teachers out there can look at something like this tomorrow morning at 8 o'clock just to get students going. You might think about the relationship between all of these graphs and try to describe the relationship between all of these graphs. For example, I see here from time t equals 0, there's a 2 right here. To time t equal 2, the velocity is positive. What does that mean? How do I interpret that? It means the particle is moving to the right. We can see that the position function is increasing here. At time t equal 2, the velocity changes to negative. We know the particle is moving to the left. We know that the position function becomes smaller. It's moving to the left. And then at time t equal to 5, the velocity is positive again. We can see the acceleration function graphed in red here. You might think about the relationship between velocity and acceleration. I think that's a nice graph. And in fact, in a minute or two, I'm going to show you another one that I think is very cool for interpreting the motion of the particle. Well, all right, very common question on the AP exam, and I'm not going to do this one, this particular problem in the way that you might be asked to on the AP exam. But how do you know when the particle is speeding up at a particular instant? How do you know when the particle is slowing down in a particular instant? While people are thinking about that one, Curtis, there was a problem on the AP exam last year, which was a little unique in asking about speed. It asked something like the following: show that the speed of the particle is always slowing down for t greater than or equal to 0, or always speeding up for t greater than or equal to 0. It was a different sort of question, not asking about a specific point. And I think it made students think a little bit more about, in general, what's the speed of this particle. So how do we do this? How do we know when the particle is speeding up, when the particle is slowing down? Let's say at a particular time, t equal t1. How do we do that? Anybody got an answer to that out there, Curtis?
I don't know. I'll wait to see if anybody puts anything in the chat.
All right, we'll hold that in abeyance just for a minute off to the right-hand side. I just, for the heck of it, just to do something a little bit different, attack this graphically. We know that the speed of the particle is the absolute value of the velocity. And so if I could graph the absolute value of the velocity, I could take a look and say, well, where is it decreasing and where is it increasing? So here's a graph of the absolute value of the velocity. Where is it decreasing? From 0 to 2. I'll put a little 2 over there. And
Wanda's got it for us.
Okay, what does she say?
Speed is increasing when velocity and acceleration have the same sign.
Beautiful. So when a velocity and acceleration have the same sign, the particle is speeding up. When they have opposite signs, it's slowing down. And just as sort of an aside here, remember that if the question does not ask you for the actual velocity, the actual acceleration, and it may, but if it doesn't,
look at that. I think we got a student response too. Increasing if velocity and acceleration have the same signs, and decreasing if the signs are opposite.
Beautiful. Excellent. If it doesn't ask you for those values, you don't have to provide them. You can only talk about the sign. Because the drawback is if you provide those values and you make a mistake, you will lose some credit somewhere along the line. All right, let me take a look at one more graph and then I'll hand it over to Tom for a minute. This here, I put a question up here and we'll leave this as open. Can you come up with an alternate method for finding those intervals that I just delineated on the previous page? We'll just leave that as an open question. And here's another way to summarize the motion of the particle. So I produced this graph that contains the graph of S, the graph of V, and the graph of A. I hope you can see all of those. They're in different colors. And I think I've got them all labeled. And as I look at this graph, I can sort of determine when is the particle moving to the left, when is it moving to the right. And I can also, by looking at the velocity and the acceleration, determine when is the particle speeding up and when is it slowing down. For example, I'm going to try to draw one vertical line in here, try to interpret one section of this graph, and we'll leave the rest to you. So I'm going to try to draw that line in at t=2 if I got them to line up. And here's a couple of things I see here. So look at the position function. It's increasing. That's an indication that the particle is moving forward or to the right. Look at the velocity and the acceleration functions. They have different signs. So that means that the particle is slowing down. So that's kind of a neat graph, very difficult to draw for me, but I think that really helps us interpret how this particle is moving on that straight line.
I agree, Steve. That's
like
a fantastic image there. I mean, that seems like one that I could print off and put up on a, use as reference just for remembering all this particle motion.
Putting it all together, absolutely.
Yeah, that's a great image.
Tom, how about a little technology? What do you say?
Sounds good.
All right, there you go.
Okay.
What are we looking at first? The 84?
Well, I'm going to start out with the 84.
Okay.
And, just kind of do some real basics for working with particle motion. So in terms of plotting on the 84, I'd suggest actually making use of the parametric plotter, even for motion along just a single straight line. A lot of people think of the parametric plotter, that's for plotting both X and Y as functions of T, but it works really nicely for what's sometimes called rectilinear motion or motion along a straight line. To do that, I mean, if you went to your Y = menu, that's going to be for your regular function plot. So we're going to want to go to mode and change our plot type to parametric. There we go. And now when we return to the Y = menu, we've got it set up for this X1T, Y1T. It's really set up for, as I said, plotting both X and Y as functions of T. Here you had motion along a straight line. I'm going to assume that straight line is the line Y = 1. Now, a lot of times in AP problems, they'll say that particles moving along at one of the axes, like the x-axis or the y-axis.
Right.
Even if that's the case for visualization purposes, I'd like to lift it off of one of the axes. So I'm going to go ahead and make Y1T 1. And then I'll go up and put in for my X1T the formula for position that Steve was dealing with. So that was 2 times T. And if you hit your independent variable key when you're in parametric, it knows that you want T. And let's see, we'll raise that to the 3rd. And then we've got minus 21 times T². And yell at me, Steve, if I mess up here on
looks good.
Formula. Okay. And finally we've got the plus 60T. So let's get that in there. 60 times T. Great. Okay, so there we've got it. And let's see, window settings. Let me go to my window now. I'm going to go ahead and enter and go to the window. This is where you can set your values for T.
Hey, Tom.
Yes. Yes,
I
sir.
did get one question that popped up in the chat.
Oh, yeah.
He asked that how you decided to pick 1 as your value above the x-axis. Is that just arbitrary?
Totally arbitrary. I just wanted some value. I didn't want the when the particle's moving right along the axis, you're on top of that line, and so it's sometimes a little harder to see, or the tick marks on the axis get in the way. So yeah, I just chose an arbitrary horizontal line.
Would it also be useful to make use of the little the ball, the tracer, if you arrow over to you know, the line type, whatever. So if you go all the way to the left of x1 of t and change that graphing type. So if you arrow to the left there,
Okay.
hit enter and change that the line type to the one with the ball on it.
Okay. Give that a
Yeah,
shot.
arrow down. Yeah, there you go. Yeah, perfect. And hit
Okay.
OK.
And then we'll hit OK.
So if you don't raise it above the axis, that ball can be helpful, but I like moving it
I do
up
too.
one onto y
Yeah.
equals 1 or something
Yep.
like that, just to see it. But this also, as you graph it, then it shows a little bit of that motion.
Very good. Okay.
Sorry, I didn't mean to interrupt your
Oh,
window.
no, that's fine.
Settings there,
That's
though.
fine. Yeah. Let's see, for Windows set, you know what? I'm just gonna let's see, we had T-min. I'm not sure there was a T interval
No, it's T
specified
greater
here.
than or equal to 0. So,
Yeah, I'm just gonna go up to 10.
okay.
T-step, I think I'll leave it. It's gonna plot a point for every 0.05 T-step. And that looks like a pretty standard window. I'll start out with that, see what it looks like. We might need to adjust that if necessary. And so let's go ahead and graph this.
Whoa.
Shot off to the right quite a bit. Actually, given the coefficients that we had, perhaps that
Yeah, I
was
was thinking 60T. You're going to need values larger
yes,
than
very
10.
much. I wasn't thinking too much there. So let's go back to our window and be a little smarter about this. Probably I'll try from I think we're always in the positive direction, it seems like. So
Well, to the right of 0 anyway.
to
Yes.
the right of 0, yeah. So -5. Yeah, I shouldn't have said direction. The direction of motion could be either forward or backwards. Let me put the X max. I'll put it at 100.
I think that will work, Tom. I think I tried 80 and 100 will work for sure. I think.
Okay. And let's put a tick mark every 10 units.
Yeah.
Okay. Now for Y-min and Y-max, I think we're okay because we're going along a horizontal line. So that should still be in the picture. All right, let's give this a graph try again. That looks a lot better.
I really like that particle moving back and forth now. You really see that.
Right, yeah.
And
So,
it shot off to the right.
Tom, that the little particle or the little ball, as Curtis called it, moving along that line. Is there any way that motion can be linked to speed, or is it just a function of your computer or your calculator? In other words, if I see that particle, that ball moving very quickly, does that mean that the speed is great? Or can I judge by looking at that the particle is slowing down?
I think in general you can. I think the qualifier would be if you had a very complicated function and you were hitting some value where it was taking a little longer to compute
Yes.
rather,
Yes.
that could be an issue. However, a way you can kind of slow down the motion, but really kind of still control and see the kind of equal space would be
Yes.
to make use of the trace feature. And then if you hit the right arrow key on the trace, that's going to move time forward.
Right.
Each time I click the right arrow key, that's going to advance time by that step size, 0.05.
Right.
So if I do that at a regular pace, that's going to give me a sense of how fast this thing's moving. So
Okay.
the trick is to do it very regularly. So I'm just
Gotcha.
going to start clicking at I'll try to be as much like a metronome as I can. Okay. And if I see the particle start to slow down, I think I will see that pretty soon. Yeah, it seems like it's not moving as fast.
It seems like it's taking smaller steps.
Exactly. So
Right.
And these are equal time intervals. So that
Right.
really does translate to it moving slower. And now it actually came to at an instant, a stationary point, right? And now it's turning around, moving backwards. And like I say, I'm just trying to click as regularly as I can, and it gives me some sense. And what's nice about this is I can stop at any point here.
Yep.
Like I said, you said there was, I think one of the time values of interest was t=5.
Correct.
And I think that was supposedly a time that this thing turned around. Now I paused there. And so if I start moving again, it was still going to the left, but at this point, it should start going to the right now. Okay. If our function's right. So let me start clicking again. There it is.
Like that.
Right again. So it's a really nice way to kind of visualize that motion. And Curtis, thank you for that suggestion on changing the way that graph appears in terms of that little ball.
We had a question that popped up. Daniel asked if you can just hold down the right arrow. And I would say on the software, if you hold down the right arrow, the first couple will be sort of slower, and then it'll kind of get to understand that you mean to hold down the right arrow. But on a handheld unit, you should be able to just push that right arrow key down and hold it, and it'll take off, and you should be able to see that motion happen. I really just like going back and letting that bouncing ball kind of retrace over the step too. That also is helpful. So
right.
These are all good ideas for the way to make that work.
Now, if I may, Steve, I'll go ahead and show something on the Nspire too.
Sure.
On the Nspire, let me see if I can get screen set up. One thing on the TI-Nspire that's kind of nice is that opportunity to have kind of multiple windows. It is true on the 84, you can have like a table and a graph on the same screen, but we can actually have, in some sense, two different graphs on the same screen in different panes of a window. And that's kind of a neat way to see both the motion of the particle and the graph of something like the velocity or position. So
that's a really nice way to see that.
So this is a TI-Nspire file that actually.
Tom, you're not showing your TI-Nspire, by the way.
Oh, thank you. Let's see. I need to.
You need to just share
either
your
share
desktop
and
or
do
just
a new one. Yeah. Thank you for catching that.
Yep.
Okay. Now, hopefully, you're looking at the TI-Nspire now. Okay.
We are.
Got it.
And so this is actually a TI-Nspire document that Steve and I had worked on not too long ago. And this one is actually set up for us to be able to define, and I should pull up my screen here. There's my keyboard. There we go.
Good. Very good.
And it's actually intended to have the velocity entered. Now, Steve actually derived the velocity from a given position function, but I'm going to go ahead and enter the velocity that we've got. I think it was 6t squared,
right?
42t, and then plus 60.
Correct.
All right. And I'm going to enter that. And now on the next page of this document, that window, what we have is a graph of the velocity function as a function of time, as well as up here at the top, it's a little horizontal line that's going to show us how the particle is moving. And these things will be working in tandem. Now, I don't like the window setting on my velocity function, so let me change that a bit. Let's see, I think I want the window settings, and I think X-min, X-max is probably okay, but it's the Y-min that we really need. I think I'm going to try like -40 to 40 and see how that looks. Okay, so that velocity function probably didn't set the scale real nicely on my window. Oops. Yes, the Y scale, I should set that at 10. There we go. And so here's that parabolic, it's that quadratic velocity function. And this was, I think, I forget which color it was on the graphs that see that. But we can see at t equals 2 and t equals 5, we've got a change in sign in the velocity.
Yep.
But what's really kind of nice here is I've got a little time slider or clicker here. And up here at the top, we're going to see this particle moving as I advance time, and it's actually leaving a trail behind. Now, Steve, you were asking about, well, how can you tell if something's slowing down? Well, here we actually have a historical record of the spacing. These are equal time increments. So when those echoes of where the point has been are the closer together, that means it's not moving as fast. And so we can see, oh, it's really definitely slowing down now, because we can see those points kind of piling up. And as I look down here on my velocity graph, I notice I'm almost right there at t equals 2. Okay, so that'll be the point where we'll see the particles start to come back the other direction. Now, what I'm not seeing on this file, and I apologize, Steve, it's something we've been working on, trying to get a file where it would actually kind of bend around, and so you can see that. And I didn't locate a file that would do that. But this is still, I think, pretty nice in terms of, oh, we've passed t equals 5 and seeing
going back the other way again. Yep.
And now it's really starting to speed up, because now I'm seeing a spacing for those equal time increments. But I think even here, if you look up here at the top, you can get a sense of how the particle moved forward, then back, and then, oh, and I should say move to the right, then back to the left, then forward to the right again. And so down here in the lower left, you're seeing a couple of different values here. This DSP is the displacement. And I think there's also a distance traveled showed. Let's see if I can. And you can see the displacement would be from my starting point to my ending point. How far have I traveled? And the distance is actually the total distance covered. So that's a different, and that's certainly a key distinction students have to keep in mind on the AP exam. One more graph here. There is a graph of the position function, also shown. That was that cubic look, and we can also do something along those same lines with seeing the motion.
You got a nice compliment here, Tom, on your display. Wanda Burns gave you a big, nice job.
Oh, she's too kind. She's too kind. But it's neat. You know, I was going to mention, I think, you know, a lot of teachers use the 84. I would encourage them, even if your students do not have the Nspires, you as a teacher might want to really take a look at it, at least the teacher software for demonstration purposes, and in class-led discussions. I think there's some
Yeah,
pretty
this
neat
is
things
really
you can
nice.
show.
Yeah.
Really nice demo here. Mhm.
So I'm going to turn it back over to Steve.
All righty. Thank you.
There you go.
Oops. There we go. How's that? Can you see that, Curtis? No, maybe not.
Not yet.
Not
But
yet.
there we go.
Sorry about that. Apologize. Let me try that again. Here we go. There we go. How's that?
Now we're getting
Now
it.
we're looking good. All right.
Well, I don't know about looking good, but
All right.
oh, you were talking about the math.
Yes, I'm sorry. Sorry. All right. Let's try a technology active question here that involves particle motion. So I'm going to try this one. I'm going to show you a couple of things on the TI-Nspire, and I understand that there are different ways to solve some of these problems. I might suggest some of those, and Tom, I'm sure, will interject some ideas here too. So we have a particle again moving along a horizontal line for t between 0 and 10. The velocity of the particle is given by, oh my gosh, this awful expression right here. The position of the particle is given by S of t, and we know that S of 0 is equal to -2. I often get asked, oh my gosh, why does ETS give us these crazy velocity functions like that? Well, two things. First of all, if you get a function like that, one of the first things you should do, students, is to take the time to enter that correctly, carefully into your calculator, into your TI-84 and Y1. You know you're going to have to use this in some way. Take the time to carefully enter that into your calculator. And the other thing is, one of the reasons we often get some crazy functions like this is because it's not integrable, or if it is, it sure as heck isn't easy, and you're not going to do that on the AP exam. So part A, let's see if we can find all the values in this interval in which the speed of the particle is 4. I'm big on, as Tom knows, I'm very big on trying to identify key words and key phrases, especially in these quote unquote word problems. So here, this problem is asking me something about the speed of the particle. What's the speed of the particle? We know that's the absolute value of the velocity. So in general, I think I've recognized, as I try to interpret this, I think I've recognized that I need to solve that expression for t. I'm going to show you a couple of ways that I can do this on the TI-Nspire. One way I can do this is to use the built-in solve function. And you know, you can almost read that right off. We as mathematicians use this notation, and it just runs right off your tongue. Solve the absolute value of v of t equal to 4 for t. And if you look real closely here, you can see that vertical bar in there, which stands for, in my mind, such that t is between 0 and 10. And this comes back and gives me these three values, which I could then say report on the exam. Here they are. And I think I usually report these as rounded, but remember, we take rounded or truncated, but we need those 3 digits to the right of the decimal. Here's another way to do that. And, you know, sometimes if I have the time, not on an exam, but I might check this, and I'm checking this on the graph screen. And I decided to do this by graphing the velocity function, not the absolute value, and the lines, let's say y equal 4 and y equal -4, the horizontal lines at 4 and -4. And so what I need to do is to find, well, where are the places where that velocity function intersects those lines? So, all right, I used the intersect feature or function on the TI-Nspire. I used it 3 times. And I think you can see my values down here. And with a little bit of luck, those are the exact same t values as I found on a calculator page. So I did it, what I would say, numerically on the calculator page, and I backed that up sort of graphically on this graph page. I like that. Here's another nice question, sort of a standard question in these types of problems. Let's see if we can write an expression that can be used to find the position, S of t, of the particle at any time t, and then, son of a gun, let's use that expression to find the position at time t equals 7. I'm going to scribble a little bit off to the side, if it's okay with you, Curtis. I'm going to write this in the following way. I'm going to write the integral from 0 to t of v of x dx is s of t minus s of 0. I'm kind of old school in the way that I think about these problems, in that I really see this as a fundamental theorem of calculus problem. And that's the way that I often start many of these problems. I understand that many people look at this and say, oh, this is net change, and that's a terrific application, an applied application here, a nice applied problem, the fundamental theorem of calculus. But here's another way to think about this. And now I'm going to solve that for s of t. And there's my general expression here for the position of the particle at any time t. Some of the students out there, well, just as a tip here, notice that we really ought to be using a different variable here for the upper bound and for the variable of integration. Now, we can argue about this all night or for the rest of the night. But from my standpoint, I think that really ought to be, or they really ought to be different letters. They really ought to be different variables. For example, here's kind of a silly argument. But if this x right here and right here were t's, and I said to you, well, what's s of 1? Well, does that mean where there's a t inside here, I put in a t equal to 1? Not really. So that's a very kind of simple, silly argument of why you need different variables in there. They're really acting in two different ways. So now if I want the position of the particle at time t equals 7, I'm just going to plug in a t equals 7. And of course, I can't find this integral by hand. I'm going to go to the calculator right below this. And I actually did this in two different steps just for my own benefit. I first found the definite integral from 0 to 7 of the velocity function. And then I added a -2 to that, so that I know the position of the particle at time t equal 7. Hard to see right here, but that's actually a 7 in there. Is 9.598. How about that? Very cool. Part C is another kind of standard question that we ought to be able to solve with technology. It says, find all the values of t in this interval in which the particle changes direction. Well, those are places, of course, where the velocity changes from positive to negative or vice versa. And I'm going to start out on the left-hand side to show you another feature of the TI-Nspire. And Tom knows that I really like this one. This is the built-in function zeros. So I'm going to do numerically here with the machine, with the calculator, what I just asked about or said. Find the zeros, find the places where the velocity is equal to 0 for t between 0 and 10, and it comes back with those two values. All right, if you really got a sharp eye here, you can look at that solution or that what the calculator returns there versus what it did for solve a minute or two ago. Right here, this circled expression is actually a list of values. So that if I actually assign that list to a name, to a variable, say, I can then refer to specific values in that list, like the first value, like the second value. I think that's a really nice feature. I'm going to back this up with my graph on the right-hand side, and I'm actually going to use my graph to finally answer this question. There is a graph of the velocity function. We saw that a minute or two on the previous page. But here's a graph of the velocity function, and what I needed to do is to find those places where it crosses that x or t axis. I feel pretty good about my answers over there on the left-hand side. There's the 6.037. There's the 8.705. And if I look at the graph of that velocity, I can see that v changes from positive to negative at this value. It changes from negative to positive at this value. Those are the two places where the particle changes direction. So I did it numerically, but I've got it backed up here with a graph. I feel pretty good about those answers. And I think I've got a part D in here. Is the speed of the particle increasing or decreasing at time t equal 5? Well, there are lots of different ways that we can do this one. Here, up above this line, here on a calculator page is numerically the way that we're kind of used to doing this, but I'm going to show you a couple of other different ways. I need to take a look at V of 5 and A of 5, and I need to look at those signs. And so I found V of 5 on a calculator page. I found the derivative of the velocity, the acceleration at t equal 5, and son of a gun, they're different signs. So that means the speed of the particle is decreasing at t equal 5. I'm going to put a little asterisk next to this one because this was kind of like a revelation for me. I hadn't really thought about this, but I think a couple of students did this a few years ago on the AP exam. And I was wondering, what the heck are they doing? And this actually works quite nicely. See if you can look at this and interpret what that expression is asking for. Find the derivative of the absolute value of the velocity, which is find the derivative of the speed. There's that vertical bar at t equal 5. Well, son of a gun. The derivative is negative. What does that mean? The speed is decreasing at that time. That's a really cool way to do it. What you should be asking, is that acceptable on the AP Calculus exam? Absolutely. As long as you tell us what you're doing, I'm taking the derivative of the speed function. Here's another way to look at this, and I've got a question that you can throw out there on this one, Curtis. Here's a graph of the absolute value of the velocity function, which again is a graph of the speed. And let's see if I've done this right. This is t equal 5. I wonder what this is, and how do I look at this graph and know that the speed is decreasing there? How would you know by looking at that graph, looking at that dot, that point on the graph at t equal 5, that the speed is decreasing? We'll leave that out there as a question, and I've got to at least start the next one because I really like this. We won't get all the way through this one, Curtis, but this is kind of a neat problem, I think. Have you been to Disney World, Disneyland?
I've been to both.
All right, so the one in Florida has this ride called the Tower of Terror. Have you been on that one, Curtis?
I choose not to go on those.
Oh, you coward.
I love roller coasters, not a big fan of the big drops.
Not this one, okay. Well, part of this is you actually get on this ride, I believe it is on the 5th floor. And this graph is actually pretty realistic. I actually did some research about this ride, and it's not always the same. So in other words, if you went on this ride 4 or 5 times, you would get a different sort of experience each one of these times. But as you walk into this ride, it actually begins on the 5th floor, and you get onto this sort of elevator, all right? And what I've got here is a graph of the velocity of this service elevator for t between 0 and 165, I think it's seconds. So t is measured in seconds and v is measured in, what is it, meters per second. And again, I think in the real ride at Disney that this ride begins on roughly the 5th floor, and that's about, we'll say, 20 meters high. So it says, at what time in that interval, if any, does the elevator change direction?
Woo. We got some Tower of Terror experts out there, by the way.
Oh, we do, huh?
Yes, there are.
Tower of Terror.
You brought up Tower of Terror, all of a sudden the chat exploded.
Lights up, huh? Well, I've got some questions for those Tower of Terror experts, okay? So first of all, when does the elevator change direction? Well, that happens with a velocity changes sign. It might be a little difficult, and I apologize for this, Curtis. Maybe I should have made that graph a little bit bigger, but it is with a velocity changes sign. Now, I think that occurs right here at t equals 65, at t equal 80, at t equal 100, and t equal to, I think that's 150. I don't think it changes direction really at t equals 60, although there might be something interesting going on there that we could talk about. All right, you Tower of Terror experts, what I want you to tell me is what's going on with this service elevator between t equals 0 and t equals 60? How about an interpretation of what's going on with that elevator over that time interval?
I mean, I can give you an idea. It begins to go up and it goes faster up for a little while, and then begins to slow down. It stops.
Okay, good. And what happens between 20 and 40?
Stops at 20 and 40 and holds position.
Holds steady.
And it does that same thing again.
Okay.
Right.
Right.
And Gabe is going with me here. He says the elevator moves up for the from that position, right? So we're doing the upward between 0 and 60. We're doing the only motion we take is up or stopping.
Okay, very good. Excellent. All right, well, let's see if we can answer a couple of other questions on this. And maybe we won't do this tonight, Curtis, but maybe we can come up with a new calculus term for this. Tom might have one already. But here's part B, and I might have to go back to the graph here. I apologize for that. At what time in the interval is the elevator the highest, and how high is the elevator at that time? Well, okay, let's see. When is the elevator its highest? At what times t do we have to check? Well, as I think about this one, this is actually looking for an absolute maximum value, isn't it? On the position function.
On the position function, right.
So that means I've got to take a look at the critical values and the endpoints. Oh, wait a minute. Before all of this works, you have to make sure that this is a closed interval. Is it? Yeah, 0 to 165. Okay. So I have to take a look at the endpoints, and I have to take a look at where the velocity is 0 or does not exist. Okay, I'm going to cheat a little bit. I know I need to look at where the velocity is 0. Here they are. Let's see. T equal to, what is that? T equal to 65, T equal to 80, T equal to 100, T equal to 1. I know I got to look there. I know I got to look at T equals 0, and I know I got to look at T equal to 160. Those are the endpoints. Now, there are a couple of places here, for sure, where I might want to check also. By the way, there are no places where the velocity does not exist because this graph is, well, defined everywhere from 0 to 165. But there might be a couple of other places where I might want to check just because, well, I asked you guys to interpret what's going on between 0 and 60. So the elevator's going up here from 0 to 20, and then it's just kind of at rest. So, you know, just for the heck of it, I'm going to take a look at what's going on at t equal 20. Now, I know, and you know, that at t equal 40, because the velocity is positive, it starts to increase, it starts to rise again. So I think maybe I want to take a look at what's going on at t equal 50. I can tell by an area argument that at t equal 50, it's going to be higher than at t equal 20. So just for the heck of it, while we're here, I'm going to take a look at t equal 20, and I'm going to look at t equal 50 because, you know, something interesting could be going on there, even though that's not really, I would say, a critical value, but I want to look there. Here we go. Here's a table of values. Here's what I got, and I'm going to throw out another question here. Here are the two that I just mentioned a minute ago that I think I really need to take a look at. 65, 80, 100, and 150 were quote unquote critical points, and 0 and 165, excuse me, were the endpoints. So, Curtis, just as sort of a general question, how do I find all of these values? I know that S of 0 was given to me as 20, but how do I find, what's the method for finding all of those values? I think I've got a little bit of a clue in my calculations here that are given, but how do I really find all of those? Can you give me an idea?
Integrate, I guess, right?
Well, that's an excellent answer, except I didn't give you a formula.
Oh, you didn't give me a function to work with.
No, I did not. That was mean, I know, but I did not give you a function.
And you did areas. I mean,
you have to do areas. You have to do areas. That's excellent. This is a really interesting one. You might think very carefully and ask your students about how do you find the position at time t equal 165. And you'll notice here that the service elevator starts on the 5th floor and ends down at the ground floor, and everybody can run out and try to get in line again. So I'm going to look at all of these values, and it sure seems like the highest that this service elevator goes is 55 meters. It happens to occur at 3 different times. And you're right. It's actually at t equal 55 for a lot of time. It's kind of sitting there, isn't it? For t between 50 and I think it's 60. So, you know, this would be an interesting question. You'll never see one like this on the AP exam, but there's really an interval of time at which it is its highest point, 55 meters. Very good. How do you find the total distance that the elevator traveled during that time interval? Well, again, you can make an area argument. We want the integral from 0 to 165 of the absolute value of V of t. I added all of these areas up, and I think I got 230 meters. And once again, if you go to Disney and you do ride this, all you experts out there, generally your ride is somewhat random. I believe there might be some, you know, some list of 20 or 30 programmed rides in there, but it's quite likely you'll get a little bit different experience every time that you ride it. Well, I think we've come to 8 o'clock here Central Time, Curtis, but we do have a question in here, and we'll post this, of course, on the website. For the BC students, we have a problem about a particle moving along a curve in the plane. And this is a nice calculator active problem also. So we'll post the answers to this one. I'll send that along to you tomorrow morning, Curtis. How about that?
All right, that sounds good. We'll make sure to get this up there. I will put my email address in the chat here real quick. It's probably going to show up before I finish saying this. I'll put my email here in the chat. For all the teachers out there that are still watching this, want to ask for some professional development material, certificate, whatever. I also will make sure that I get the teacher document posted in the description for this session tonight. And you can also email me if you guys would like a copy of that TNS file that Tom was showing. Be sure, happy to make sure that you have access to that. And I'll also, if you email me and ask, I'll also send you a link to another couple of those particle motion TNS files that we have posted on the TI website. So there's a
Curtis,
number of ways to check those out.
I will also send you the file for the next Monday Night Calculus, which is
correct
volumes. So that will allow you to post that and also give you a little extra time to work on those problems. Okay?
That's right. Oh, well, yeah. So I'll be able to do my homework a couple of weeks.
There you go.
Yeah, I will be posting the problems for 2 weeks from now session. So we'll be able to have those out there for you to use with your students, or students, if you want to just go in there and get some good practice problems to try ahead of time and then log in again next 2 weeks from now. That would be great. We will be on again on March 20th, same time, same place. So look forward to chatting with you then. Good night, everyone.
Thank you, Kurt. Thanks, Tom.